Hello students, this is Mr. Allen here, and today I want to show you the epsilon delta definition for limit. And the book refers to it as a formal definition, and that's because there are actually there's more than one way to define the formal definition of limit. We're only going to be looking at the epsilon delta definition. So, in class I've been using kind of the term a predicted y value for limit. It's probably a little bit better to say that if f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. That's a lot of words, but that's what it is, and this is an informal definition, which we'll talk about more in a minute. This is an informal definition. The reason it's informal is because we haven't defined what arbitrarily close to L means. We haven't defined what x approaches c means. The first mathematician to rigorously prove this or set up this paradigm for determining limits was a mathematician by the name of Cauchy, and he is probably I think he's like the forefather of modern analysis, which is the study of calculus and basically how do we know all these things in calculus are true. And his standard is still used today. So here is the definition. It's kind of a little overwhelming. I'll read it to you. It says, let f be a function defined on an open interval containing c, except possibly at c. In other words, there could be a hole there. Let L be a real number. This statement that the limit of f of x as x approaches c equals L means that for every epsilon greater than 0, there exists a delta greater than 0, such that if, and this is basically this 0 less than the absolute value of x minus c less than delta, that's basically saying that as long as I am delta away from c, then the absolute value of f of x minus L is less than epsilon. In other words, this is saying that the limit is epsilon away from the value of the function. It's a little rough. This is kind of hard to wrap your head around. It's actually hard for me to explain. This is I've actually remade this video a few times. So what this is saying is, say we've got some function here. Let's call this function f of x. And let's say that we have established that, by the way, this is what we're looking at. The limit as x goes to c of f of x equals L. So here's L, here's our function, here is c. Remember, c is just an x value. What the definition is saying is as follows. For every epsilon, okay, so you give me an epsilon. Doesn't matter what it is, it just has to be greater than 0. Epsilon away from L, so you've got a band of values within epsilon away from L, then there exists a delta that gets you inside of that band. So let's say that epsilon here is 7, and you tell me, I'm sorry, that L is 7, and let's say that epsilon here is, let's just keep it simple, 0.1. So that means that this value up here would be 7.1, this would be 6.9. I am telling you that I could give you a delta that's greater than 0, that's going to get me inside that band. Okay. Now notice, if I provide this delta that's just drawn here, I'm not telling you what the value is because I don't know anything about the function, but you'll notice if I do the lower extreme of that delta, notice that it's above the lower extreme for L minus epsilon. If I was in the upper extreme, again, notice that I am still within epsilon away from L. So that's the key idea. So now I'm going to try to do an example to kind of illustrate this. So we're going to look at this very simple function here. And remember, this is f of x. And you probably already know that 2x plus 3 is a linear function. There's no holes. It's continuous, all those wonderful things. So you could probably already guess what this limit is. My guess is you already know that by direct substitution, the limit of 2x plus 3 as x goes to 1 is going to be 5, and it is. In fact, we could look at a picture, which we will here in a minute, to see what that is. So in this example, we know that L is 5. We know that f of x, 2x plus 3. We know c is 1. So the definition says that for each epsilon greater than 0, there exists a delta. Now I'm going to focus on this part right here. Okay, I'm going to focus on this part here first. So I'm going to say that f of x minus L, which would be, well, f of x we've already established is 2x plus 3, and L is 5, so we were going minus 5. So that'd be what, the absolute value of 2x. In fact, let me not do that yet. Let me do that down here below. So that's going to be the absolute value of 2x minus 2. And then we could even factor out a 2 there, and we could say that it's x minus 1. Okay? I'm going to erase what I did over here. Remember that over here on the right, this is epsilon, and this should be less than epsilon. Okay? So again, this is at less than epsilon. And I guess even furthermore, I could do one more step here, and I could say that equals, oops, I'm getting too close to this stuff over here. I'm too close to the bottom. X minus 1 is less than epsilon over 2. And I've done a bunch of work there, which you were probably thinking, okay, great, Mr. Hunt, I'm not sure why you did all that. Here's why I did it, though. So I'm going to use a different color. Now let's go back up to this equation, or inequality. It says 0, and by the way, this was also greater than 0. It's 0 less than the absolute value of x minus, now what was c? C is 1, which has to be less than epsilon. Oops, delta. Just screwed that up. The stuff that we just did was epsilon. This is the delta part. The equation is delta, right? So we're dealing with this right here. Now here's where things get very interesting. What do you notice about this expression here and this expression here? Well, they're both the absolute value of x minus 1. That means I can substitute them. In other words, what I'm telling you is that I could say that epsilon over 2 is going to be less than delta. In other words, what I'm actually going to say is, or I could even switch it around, right? I'm telling you that whatever delta, whatever epsilon you give me, I'm just going to make my delta epsilon over 2. This actually should be like an equal sign. See how this is less than here? So this is going to be equal sign, and when we translate this over, that's going to be equal. So I can substitute this in. So this is, and I wrote it backwards. So that's actually, you know what? Let me write that. Let's go back here and correct this, make this look better. So I can substitute this in. We'll do it. Let's do it in green again. So these things. So this is less. Let's take this over here. Absolute value of x minus 1 is less than epsilon over 2. So I can basically say that delta has to be less than epsilon over 2 because these two things I've circled in red are equal. Okay, so I'm kind of actually, I think maybe a better way for me to say this, I was putting this over here. So as long as I pick my delta to be less than epsilon over 2, I win. Okay. Now I know that I've done a lot of things that you're maybe not quite sure why I'm doing them, but here's the thing. So let's say that Mr. Allen tells you that, and I don't know if I got anything on this slide. I don't. Okay, good. Let's say I tell you that the limit as x goes to 1 of 2x plus 3 is equal to 5. You say, no, Mr. Allen, that's not true. I don't believe you. Okay, fine. You don't have to believe me. Now remember, I've already done the work now, and I already know that I'm going to pick my delta to be epsilon divided by 2. So again, our definition tells us that for each and every epsilon greater than 0, there exists a delta greater than 0 that's going to satisfy all of those conditions. Okay, fine. So I'm going to say, you don't believe me that this limit's 5? Give me an epsilon. And you're like, okay, well, fine. So you say, let's say that you say, okay, fine, Mr. Allen, I'm going to say epsilon is equal to, let's say 0.01, which is 1/100th, which isn't very small, but it's greater than 0 and it's positive, so it's fine. So here's what I'm going to do now. So Mr. Allen is going to do the following. Mr. Allen's going to say Well, delta needs to be less than epsilon over 2, and in that case, that's going to be 0.01 divided by 2, which is equal to 0.005. So all I need to do is pick a delta that's less than 0.005. Fine. So I pick my delta to be 0.004, which I hope you would agree is less than what it needed to be. And now you might be saying, okay, what the heck, Mr. Allen? So here's the deal. I'm going to go to the next slide here, okay? So remember this. You picked this for your delta, or your epsilon. I picked this for my delta. So on the next page, I've got a graph. So remember, epsilon was chosen to be 0.01. Delta was chosen by me to be 0.004, okay? So, and we said that the limit here was 5, c was 1, okay? And here's our function f, right? Okay, so here's 1, 1's right here. And epsilon is 0.01. Now 5, by the way, I'm going to draw 5 up here. Here's 5. So what would be 5 plus 0.1? So this band up here would be 5.01. And then this band right here would be 4.99. Okay? Now, so when you challenged me and you said epsilon is 0.01, basically what you're saying is, okay, I don't believe you that the limit is 5. And so, okay, fine. You pick an epsilon, you pick that. So I now have to provide a delta, which I've done, that's going to get me within that band. So here we go. So remember, our function is f equals 2x plus 3. Our c value here is 1. So what I need to do is I need to show you that as long as I'm within 0.004 of 1, I'm going to be within that range you gave me up there. So let's see what c plus delta is. Well, 1 plus that is going to be 1.004. Now I'm going to use my calculator to figure out what f of c plus delta is. So I'm going to do 2 times 1.004, and then I go to add 3, and I get 5.008. By the way, 5.008 would be right there, which is less than 5.01. Okay? By the way, I could have done c minus delta, and it would have given me a value right in here. Now, I hope if we played this game enough, you would realize it really doesn't matter what epsilon you tell me. You could pick 0.000000 with 20 zeros and then a 1, and I'm still going to win, because all I'm going to do is I'm going to take your epsilon, I'm going to divide it by 2 and pick something slightly less than that. So here's what, if this is the subtle thing, I want you to think about this. This was arbitrary. You could have picked anything you want, and I know I'm going to win. That's how I know the limit's 5. Okay, now the video is getting long here, and I've done one example. I'm going to show one non-example. If you can bear with, I want to show you an example of when this isn't going to work, when the limit isn't going to be in whatever it is. Okay, so that's and I guess I should finish this and say, therefore, the limit as x goes to 1 of 2x plus 3 is indeed 5. Now, you may not feel convinced, but I am convinced that that is the truth. So let's look at a non-example. So the function here, I'll call it g of x. The function here is the absolute value of x over x. Now this is not a super familiar function for most students. The c value we're looking at here is 0. And I'm telling you that this, first of all, I'm going to tell you that g of 0 is d and e. It doesn't exist because you have 0 over 0, so it doesn't exist. I'm telling you that the limit also does not exist. So here's a picture of the function. It's in red. and I used Desmos to graph this. There'd actually be a circle there, an open circle there, an open circle there. Now I want you to think about what we talked about. Remember, we talked about epsilons, those corresponded to the y values, and then deltas, those corresponded to the x values. So let's say we play that game again, except this time I'm going to let you be the loser. So let's say that you think the limit is 1. Okay, by the way, this is wrong. I'm gonna put a big X through. This is not true. But let's say you thought the limit was 1 and you're like, Mr. Allen, the limit's 1. Prove that I'm wrong. Okay, because you see right here, this y value, remember this is the y value, this y value, the limit's 1. Okay, fine. The limit's 1. I'm going to pick an epsilon, and the epsilon I'm going to choose is 0.2. I'm going to pick 0.2. And now you've got to come up with a delta that's going to get me within 0.2. It's not going to work. The problem is remember, C here is 0, right? We said C was 0. So you have to somehow be able to guarantee that you can give me some delta that's going to get me within 0.2 of epsilon. The reason that's not going to work is, how far is it between these two curves? This one here and this one here. How far is that? That's 2 units away. So let's say you get your 0.2 over here on this side. Let's say you get this part up here. Okay, so it's a check over there. But what about on the other side here? So if you're okay over here, you're going to miss over here. There's no way you're going to be able to find it. Now, honestly, if you picked an epsilon, if I gave you an epsilon that's bigger than 2 or bigger than 1, let's say, bigger than 1, it's going to be, so you can do that. All I got to do is pick my epsilon to be less than 1 and I win. Again, this is, I think I'm going to stop there. If you're not quite following me yet, I would encourage you to either watch this video again or maybe look up another video on YouTube. This is why it's optional. This is pretty challenging stuff. And you notice I only used a linear function. I didn't use a quadratic function or something more complicated. It's actually pretty hard to use it. But if you understand it, it really does help you understand what limits are. So I'm going to stop it there.